Assalamu alaikum students, first year. Today we will start chapter number 4, liquids and solids. And the topics today are factors affecting London forces and hydrogen bonding. Factors affecting London forces. The definition of London forces. The momentary force of attraction. The momentary force of attraction created between instantaneous dipole and the induced dipole is called dipole-induced dipole interaction or London forces. Students, it is a very short-lived attraction because the electrons keep moving. This movement of electrons causes the dipoles to vanish as quickly as they are formed. Anyhow, a moment later the dipole will appear in different orientation and again weak attractive forces develop. London forces are present in all types of molecules, whether polar or non-polar, but they are very significant for non-polar molecules like Cl2, chlorine, hydrogen, noble gases like helium, neon, etc. Now we will discuss factors affecting the London forces. First factor is the size of electronic cloud of atom. When the size of atom or molecule is large, then the dispersion becomes easy and these forces become more prominent. Elements of zero group in the periodic table are all monatomic gases. They don't make covalent bonds with other atoms, and because their outermost shells are complete, their boiling points increase down the group from helium to radon. The atomic number increases down the group and the outermost electrons move away from nuclei. The dispersion of electronic clouds becomes more and more easy. So the polarizability of these atoms go on increasing from top to bottom. Polarizability. What is polarizability? It is the quantitative measurement of extent to which electronic cloud can be polarized or distorted. Distorted means distorted is called where shape is disturbed of atom. This is called distorted. When we say that species, atoms, ions or molecule is polarized, it means that temporary poles are created. Temporary poles are created. This is possible if electronic cloud can be disturbed or distorted. Here distorted and disturbed same meanings. The increased distortion of electronic cloud creates stronger London forces and hence the boiling points are increased from down the group. And fluorine is a gas. Fluorine is a gas and boils at minus 181 degrees centigrade. While iodine is a solid at room temperature, which boils at 184.4 degrees centigrade. Polarizability of iodine molecule is much greater than the fluorine. Another important factor that affects the strength of London forces is the number of atoms in non-polar molecule. Greater the number of atoms in a molecule, greater the polarizability. Direct relationship between number of atoms and polarizability. Let us discuss the boiling points of saturated hydrocarbons. These hydrocarbons have chain of carbon atoms linked with hydrogen atoms. Compare the length of chain for C2H6 and C6H14. They have the boiling points minus 88 and 68.7 respectively. This means that molecule with a large chain length experiences stronger attractive forces. The reason is that longer molecules have more places along its length where they can be attracted to the other molecules. Okay students, this was the topic factors affecting the London forces. Now we will move towards the next topic, hydrogen bonding. Hydrogen bonding, the definition. Hydrogen bonding is the electronic force of attraction between highly electronegative atom of one molecule and partial positively charged atom, hydrogen atom of the molecule. And the electronegative atoms responsible for creating hydrogen bonding are fluorine, oxygen, nitrogen, and rarely chlorine. The strength of hydrogen bond is generally 20 times less than that of covalent bond. It is a weak bond as compared to covalent bond. And it is not advisable to limit the hydrogen bonding to the above mentioned electronegative atoms. 3 chlorine atoms and chloroform are responsible for hydrogen bonding with other molecules. Here, this is the example of hydrogen bonding in water, where dotted lines show the hydrogen bonding between oxygen atom of one molecule and hydrogen atom of other molecule. This is another example, hydrogen bonding between chloroform and acetone. This is formula chloroform CH3 and acetone C double bond of CH3 CH3. Now we will discuss the another example also. Hydrogen bonding present in molecules of ammonia and those of hydrogen fluoride can be depicted. The molecules of HF join with each other in a zigzag manner. The exceptional low acidic strength of HF molecule as compared to HCl, HBr, HI is due to this strong hydrogen bonding because the partial positively charged hydrogen is entrapped between two highly electronegative atoms. Okay students, now we will discuss the properties and applications of compounds containing hydrogen bonding. Thermodynamic properties. First of all, we will discuss thermodynamic properties. Hydrogen bonding exists in compounds having partial positively charged hydrogen and highly electronegative atoms bearing partial negative charge. Obviously, such intermolecular attractions will influence the physical properties like melting and boiling points. Let us compare the physical properties of hydrides of group 4th, 5th, 6th, and 7th. The graphs are plotted between the period number of the periodic table on x-axis and boiling points on y-axis. The boiling points of hydrides of group 4 convinces that they have low boiling points as compared to the groups of 5th, 6th, and 7th. The reason is that these elements are least electronegative. CH4 has the lowest boiling point because it is a very small molecule and its polarizability is the least. Yes, students, when we consider the hydrides of group 5, 6, 7, and 8, then ammonia, water, and HF show maximum boiling points in the respective series. The reason is the enhanced electronegative character of nitrogen, oxygen, and fluorine. That's why water is liquid at room temperature, but H2S and H2SE are gases. It is interesting to know that the boiling points of water seems to be more effectively affected by hydrogen bonding than that of HF. Fluorine is more electronegative atom than oxygen. So we should expect hydrogen bonding in HF to be stronger than in water, and as a result boiling points of HF should be higher than that of water. However, it is lower, and reason is that the fluorine atom can make only one hydrogen bond with electropositive hydrogen of the neighboring molecule. Water can form two hydrogen bonds as it has two hydrogen atoms and two lone pairs are on oxygen atom. Okay, number 2, solubility of hydrogen bonded molecules. Solubility of hydrogen bonded molecules. Solubility takes according to the rule like dissolve like. If the solute is polar, then it will dissolve in polar solvent, and if the solute is non-polar, then it will dissolve in non-polar solvents. like dissolve light. Water is best example of hydrogen bonded system. Similarly, ethyl alcohol also has a tendency to form hydrogen bonds. So ethyl alcohol can dissolve in water because both can form hydrogen bonds with each other. Similarly, carboxylic acids are also soluble in water if the size are small. Hydrocarbons are not soluble in water at all because they are non-polar compounds. All hydrocarbons are non-polar, they do not dissolve in water because water is polar, and there are no chances of hydrogen bonding between water and hydrocarbon molecules, therefore they do not dissolve. Number third is structure of ice. Structure of ice. The molecules of water. Number third is properties of hydrogen bonded molecules. The structure of ice we will explain here. The molecules of water have tetrahedral structure. The molecules of water have tetrahedral structure. Two lone pairs of electrons occupy oxygen atom. On oxygen atom occupy two corners of tetrahedron. Look here, this is tetrahedral structure, and this is HOH water molecule, and these two sides occupied by electrons, lone pair of electrons on oxygen atom, and this is tetrahedral structure. Angle is 109.5 degree, and in the liquid state, water molecules are extensively associated with each other, and these associations break and reform because molecules of water are mobile. When the temperature of water is decreased and ice is formed, then the molecules become more regular, and this regularity extends throughout the whole structure. Empty spaces are created in the structure. That's why when water freezes, it occupies 9% more space and its density decreases. The result is the ice floats on water. This is also answer of short question. This is very important. The structure of ice is just like that of diamond because each atom of carbon in diamond is at the center of tetrahedron, just like oxygen atom of water. The lower density of ice than liquid water at 0 degree centigrade causes water in ponds and lakes to freeze from surface to the downward. In ponds and lakes, freezing takes place from surface to downward. Water attains the temperature of 4 degrees centigrade by the fall of temperature in the surroundings. As the outer atmosphere becomes further cold, water at the surface becomes less dense. This less dense water below 4 degrees centigrade stays on the top of slightly warm water underneath. A stage reaches when it freezes. This layer of ice insulates the water underneath for further heat loss. Fish and plants survive under this blanket of ice for months. This is the reason how animals in water in cold areas survive. Number fourth, properties of hydrogen bonding in compounds. Number four, cleansing action of soaps and detergents. Cleansing action of soaps and detergents. Soaps and detergents perform the cleansing action because the polar part of their molecule are water soluble due to the hydrogen bonding, and the non-polar parts remain outside water because they are alkyl or benzyl portions and insoluble in water. Number 5. Hydrogen bonding in biological compounds and food materials. Hydrogen bonding exists in the molecules of living system. Proteins are important part of living organisms. Fibers like those found in the hair, silk, and muscles consist of long chains of amino acids. These long chains are coiled about one another into a spiral. This spiral is called a helix. This spiral is called helix. Such a helix may either be right-handed or left-handed. Right-handed or left-handed. In the case of right-handed helix, groups like NH and C double bond are vertically adjacent to one another, and they are linked together by hydrogen bonds. Hydrogen bonds link one spiral to the other. X-ray analysis has shown that average there are 27 amino acid units, and deoxyribonucleic acid DNA has two spiral chains. This is the structure of DNA, two spiral chains. These are coiled about each other on a common axis. In this way, they give a double helix. This is 18 to 20 angstrom in diameter. They are linked together by hydrogen bonding between their subunits. And last one is hydrogen bonding in paints, dyes, and textile materials. One of the important properties of paints and dyes is the adhesive action. This property is developed due to the hydrogen bonding. What is adhesive action? The sticking of these materials, paints and dyes on the surface, this is called adhesion. This property is developed by hydrogen bonding. Similar type of hydrogen bonding makes glue and honey as sticky substances. All sticking substances show hydrogen bonding. We use cotton, silk, or synthetic fiber for clothing. Hydrogen bonding is of vital importance in these thread making materials. This hydrogen bonding is responsible for their rigidity and tensile strength. Okay, students, next we will study further topics of this chapter, crystal topic, inshallah. Okay, thank you so much.